mass. These, and these the first three. Yeah, that's what I was working on. And if I open the bookmarks, when I have the bookmarks, when I have the bookmarks, I should clean that up. It's a mess. Dollar here. What? That's not what I wanted. Bookmarks. Workspace, that's what I wanted. So I kind of realized, I realized where it's all these going. So I was taking a look at the paper the other day, and that is way better, because now I understand where these, where these comes from. So this is because the algorithm is also designed to solve for systems of equations where that are not just real numbers, but also have complex numbers. And so the whole idea with the Harmonic test kind of works, if you wanna, so you kind of have to separate the problem into two. So you first solve for the real numbers, then you solve for the complex numbers. And when you solve for the complex numbers, you need to add this little phase shift in here. The reason, I guess, intuitively being that so if you get into the plus state, right, and this is the block sphere here. So this is an S gate, right? So this is a pi, like a. So that takes you. So that takes you, right, in the plus I or minus I, where this is all. Oh, here you go. So there's an S sharp in here. So that kind of takes you, yeah, I should set up the buttons. So that takes you basically, so you're going all the way until here, right? And so the idea, we can try to take a look at, because the idea is now those controlled operations will kind of basically move you like along this part, right? So just between these, like plus I minus I, and in the when you do this on the real part, they just move you through this part in here, right? Is that correct? Okay. What am I doing? I'm just clicking everywhere. Quantum machine learning. Okay. So this is these, right? Because they say in the paper, they say the Harmonic test is to compute the coefficients, you calculate the inner product. This is the phase gate in the color box is excluded when calculating the real part and included when calculating the imaginary part. And Harmonic overlap. So let's take a look at this, because so test used to compute the coefficients defined in 17. The overlap circuit is indicated in the dash box. So the overlap, why this doesn't work? I'm trying to, because I have one of those pens to kind of do the drawing, but the buttons don't seem to remember the configuration that I give them to switch between the painting tool and the other tool. So this is the overlap. Let's take a look at these, because to be honest, I think intuitively that's kind of what I would do in a stupid way if I would think if I would kind of think about how to solve the problem. Is I would calculate. So I would calculate, and it's kind of, it seems like that's what they're doing here, right? Like this register is calculating U. So U is what kind of, let's recap. So you've got your matrix A, you've got your ket X, and then you've got like the ket B. And so U is what prepares the B state. So this is U. Yeah. And what we're doing here somehow is we're trying to calculate these, but not exactly that, because what the algorithm is doing is it's kind of coming up with a way to calculate the cost function that doesn't require to actually do the multiplication. So you just kind of need to compute those elements in here, and they end up being projections to the zero state. And I think that's why the Hadamard test is being used, because that's what the Hadamard test is doing. The Hadamard test is projecting, is it? So if I, let's open a quirk. Let's do a quick test idea here. So if I, if I go to the plus state, now in the plus state, the projection onto the Z observable, I hope I'm using the right words, kind of, in this case is a 50-50. I mean, I don't know if you call this, it's 50-50, yeah. So you call 50-50. So if you do the Hadamard test, would basically, which by the way, you like, maybe an easy way to see the test is if you reverse, because at the end of the day, it doesn't matter, right? So what this is doing is, it's kind of it's really copying that part up here, right? So, so it's 50-50. So now the actual expectation value here, it's going to be like 50% of the times 0, and it's going to be 50% of the times 1. Now this is, I think, right, this is the this you replace with a 1, and this you replace with a -1, or the other way around, right? But whatever, it's kind of 0, right? So 0 is the expectation value, because that's kind of, it's in the middle, right, between 0 and 1, I think. I don't know if I'm using the right words and concepts, but the idea is that that's the reason why you calculate it with using a Hadamard test. Because you could also, what I kind of thought is, you could also just do, why don't you just go brute for, like, why don't you just go and, like, you come up with this circuit that computes these, and so you just, you prepare your ansatz that is kind of a possible XCAT. Then you apply this operation, right? Let's assume we have it, right? Like, let's assume we have the box, and on another register you use U to compute these, and then you kind of try to see how equal they are. And there was a test. There was one thing. I don't know if this is called. I don't know if this is the swap test, but there was one mechanism to try to see how different the states are. And I don't know if this is not what this is trying to do, right? Because it's a bunch of control nodes, and then I'm assuming a bunch of Hadamards as well. So if I go here, play the circuit. So let's just have 2 registers, okay? So I'm just gonna have some register. Just do this just so I can. So this is one register. This is another register. Let's say this register is initialized at 111, and this is 000. And if I do the overlap test now, what is it going to tell me? So if I'm going to do this part here, so if I do control not, control not, control not, and Hadamard, is it Hadamard everywhere? Oh, no, it's just in the first register, yeah. So what is this telling me? So this is telling me, this should somehow tell me that they are not equal. If, no, that's also not, if they are equal, it's still 50-50. How does this work? The Harmonic overlap test used to compute the coefficients defined in 17. The overlap circuit. of reference 55 and 56. Swap test. Okay, that's a swap test. So can I just open the PDF directly, or do I have to pay? What is it? PDFs. Waiting. Come on. Okay, but that's a swap test, right? So if I remember well, because that's exactly what I remember. So swap test. Swap test. It's a control swap. It's a precision computation used to check how much two quantum states differ exactly. Consider two states. After the harmonic state, the state of the system is the control circuit transforms the state into the second harmonic. If they are orthogonal, then the probability that 0 is measured is 50%. If the states are equal, then the probability that 0 is measured is 1. Okay, so but there is the but is this overlap test based on that? It seems to be a different thing, doesn't it? Isn't it? It seems to be a bit of a different thing. Because it's kind of not using an extra ancilla qubit. It's I don't know if this is really what this is doing, but that seems the overlap harmonic overlap test, isn't it? Why they call it that? Either are okay, but those are the references really, and I think that takes you there. 56. Learning the quantum algorithm for state overlap. Swap test and Hung-O-Mandel effect are equivalent. Swap test. Can I not just... come on. Can I just find this somewhere for free? ResearchGate. That's not these. To unknown states, nature, to find difference, configure printing, swap test, equivalent. This is all. And I cannot find this anywhere else. And this one, I think I've seen this before. Rings a bell in Archive. Okay, so that is available. What does this paper tell us? I'm looking for a second. Ancilla qubits, data qubits. No, yeah, I mean it's these. Okay, so the algorithm. Ancilla-based algorithm generalization. Okay, so look at these. So there is there it is. Our Bell basis algorithm obtained by minimizing the cost for the resources. So this is sort of an optimized version of it. Interesting. So everything goes in here. But how do you interpret the result? So that's the Bell basis algorithm. Hardware-specific algorithms, testing our algorithms. Conclusions. So there is it's a bit of a different version of it. That is, but how do you interpret the results? Let's take a look at these. shows BPF for unqubit states. The circuit employs one CNOT gate followed by one Harmonic gate with both qubits being measured. It is straightforward to show that this corresponds to a Bell basis measurement. The post-processing is a bit more complicated, with C being 1, 1, 1, 1, 1, minus 1, which corresponds to summing the probabilities for the 0, 0, 0, 1 and 1, 0 outcomes and subtracting the probability of the 1, 1 outcome. The above post-processing is equivalent to measuring the expectation value of a controlled Z operation. So the generalization is given. Okay, so the post-processing is a bit different. The total number of gates, okay, yeah, but how is the post-processing then? Our Bell basis algorithm obtained by minimizing the cost for the resources shown in figure 3, C, D, and A when rho and whatever are 1 qubit states. We obtain a circuit with one CNOT followed by Hadamard and measurements on both qubits. With a post-processing vector, C equals 1, 1, 1, minus 1. What is these though? Okay, 1, 1, okay. So the CNOT and the Hadamard gates from a building block that is used to generalize the algorithm for input states. Cross linearly with n, and positive vector can be written as into pairs from. So what I should do is, which corresponds to summing the probabilities. Okay, so you sum the probabilities, but then, and then you subtract the ones from 1, 1. That's interesting. I don't know why. Okay, this is the equivalent. Sorry, this is the equivalent of measuring the expectation value of a controlled Z operator. The generalization of this algorithm. Yeah, but then what do you do with the result? Like, how do you know? So let's go and say that I've got these in here. So this is a more optimal version of the swap test. So if you do these, so now they're parallel, right? Like they're equal. So what are the probabilities? I should take a look at the chances, a chance display, and see that. So if I but I don't get it. How do you okay, so you subtract, so you actually, if you have more than 2 qubits, more than 1 qubit, sorry, than 2 qubits, then you need to scale that like that times n, like not times, but like to the power. Okay, so if one orders the qubits into pairs from I guess intuitively, if you where am I? So if we're now I'm gonna get rid of 1 qubit because it's gonna make things easier to read. Okay, so the more different these things are, right? I don't know, let's say it's plus plus and this is minus minus, so they are like literally opposite. Okay, so it looks like these. 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1. So somehow you calculate the expectation value of a control Z. Like, so how to do that? Where am I? Here. But how do you know? How do you know how close they are? Cost of the resources. 6 of these gates are combined to create a building block. Independent of the problem. The post-processing is a bit more complicated, which corresponds to summing the probabilities for the 0001 and 10 outcomes and subtracting the probability of the 11 outcome. Let's go one level lower. Let's see if I get rid of these and I get rid of these, right? And it's just as2. So if I so here we get a 0. You subtract that and you get, so this is 50% probabilities of these and these, and that's 0, because they are completely opposite. If this would be plus, then those things add up. Okay, but how does this tell you, for example, what if I do like a T or something? Look at these, of course. So now you would have, can I open the calc? So now you'd have like 0.42 plus 0.073 plus 0.0 no 42. Okay, I'm missing like a 7 or something, and so you've got these, and now you do minus 0.073, right? And so this tells you, I guess this tells you how similar they are. Interesting. That's a cool way to do that. So so the question is, how does this scale with the qubits? And I need to figure out. It's just I need to figure out how does this post-processing vector look like. So basically, this would be this. If I would now say, please go to like S, right? So now you basically have 0.5. So they are more different. Nice. Okay, I get it. If I add another S, yeah, now we're at 0. If I add another S, nice. Cool. Okay, so this is really neat. Now, how do we do this with, say, 2 qubits, right? So we are gonna now have. Can I copy a row? No, I can copy columns, but I cannot copy a row. So I can. What do I do? What am I doing? What am I doing? What am I doing? What am I doing? So good. So basically, so what if I do, for example, what was the idea? Was it like, sorry, like these, and like these, like these? But wait a second. First of all, let's try to understand why this works. I'm just curious about these. So, okay, so this works because if they are the same, right? If they are the same, let's say 1, 1, right? The control node is basically going to XOR them. So in this case, it's going to make them different. And you want the measure of being the same to actually give you. I guess that's what you want, is if if qubit 0, it's kind of the same as qubit 1, right? You want the measure to be 1. If they are like completely orthogonal, you want the measure to be 0. And that's the idea, right? So what you do here is, yeah, and actually it's easy to see that if you scale the system with more qubits, you can break it down to do this for each qubit, because at the end of the day, if each qubit is the same, then your overall state is the same, right? I think so. In this case, so if you've got like a plus and so if you've got like a 1 and a 1, right? Or if you've got a 1 and a 1, for example, 1 and a 1, right? So what this is going to do is going to turn this off, and so then you're kind of left with the state 1 0 1 0. So yeah, 0 0 0 1, because this is 0 for sure. It's definitely never going to be 1 1 if they are the same, because if it's 0 0, it's pretty smart. It kind of stays the same. If it's 1 0, there's always a 1 1 component. That's really nice. Interesting. Come on. Stupid pen. Yeah. So this is designed in such a way that whenever this component is there, it means you kind of subtract it and you get the 0. That's what you want. And so in theory, because this all works from a sort of a linear combination kind of way, it will work for everything in between, right? Because if what you have is like a 0 and say plus, right? That component subtracts with that component, then subtracts, kind of cancels out with another one, and so all you have is left is like a 0.5 if you do that. Yeah. Okay. And that's somehow the expectation value of a control set. That's interesting. But that's a nice way to measure these. And so with multiple qubits, you would kind of do that with each qubit. And then you would add all of them, I guess. Or you would multiply all of them. No, you would add all of them. So if I have say 2 qubits, right? And I'm going to measure the whole thing. And so when there is 0 0, the same thing here happens, right? Okay, I would have to measure only. So what if I move this here? No, I move this here and I move this here. So that kind of I just mix the cables, okay? So here you've got like the first qubit and the first pair of the first register. If this is register, if this is one register and this is another register, this is the first pair of each registers. Or I don't know if I just confused it more, but I just mixed the cables. So yeah, so in this case, it will be the same kind of like those things go off, right? But in this case, it's these what we're looking for. Sorry, but it's badly represented here, but that's what you want. And if here you have like a 1, right? These things they cancel out exactly. So you do that per each qubit. Because if the first qubit is the same, right? Say 1 1, or 0, 0. And this is different. So then what you get is this is better. Yeah. So here you get like a 0.5. Here you get like 0. Yeah. So if you sum those things, then you kind of have 0.5. So ideally, what this is telling you is that yeah, they're kind of the system in this case, because remember I mixed the cables, okay? So this actually goes here and this actually goes here. So we had like, so we have these, which is 0, 0 and 1, 0, right? But shouldn't it be 0? So you should multiply that, because you know, it's kind of like if you've got, so your basis vectors here is 0, 0, 0, 1, 1, 0, 1, 1. So if you, those are all orthogonal to each other, right? So you need to multiply. You kind of need to multiply. That's the idea, I guess, because that's what they say here. Okay, I've probably spent too much time on this already, but if one orders the qubits into pairs from each of them, now I understand. Okay, so this here, this is what I was trying to do. So you do that, you do the same thing, but for each pairs of qubits, and you need to multiply. So that would be actually 0. Yeah. So here they'll be totally different because they're orthogonal to each other in that basis. Yeah. Okay. Okay, now I get it. So where was I though? Here, no, here. So now I get, but yeah, that's my whole point all the time is I would kind of rather approach this by figuring out a way to represent the matrix A, kind of multiply these. Like why? My question is, why isn't this a north of a cost function? As a cost function. Why do we need that, like that Hadamard test things in here? You know what I mean? So I would, if I was able to figure out how to implement A, then I would just have a circuit that does, I would just find a circuit that what it does is like, it prepares this thing in a box, then it applies A, and then you have another register where you have got U, and so here you do the overlap test, and there you go. Because at the end of the day, what you're doing is you're solving for these, right? And so you want to see how much these overlaps with these. Define it 17. So what is, you know what I mean? So that's my question is like, why? I get it that I get it that it probably decompose A into a circuit kind of kills the purpose of it, but still, why is then the overlap test used? What are the equations in 17? Just to calculate these, it feels like an overkill. Like if you're already using that, I think that should be enough for your cost function. Cost evaluation. In principle, all the aforementioned cost functions can be efficiently evaluated using the Hadamard test circuit and simple classical post-processing. However, in practice, care must be taken to minimize the number of controlled operations in these circuits. Consider evaluating the term, which can be written as, you know, these and these with this, meaning that there are different beta LL terms that one needs to estimate and which can be measured with the Hadamard tests. The Hadamard test involves acting on V, on 0, and then using an NCL as a control qubit, applying 0 followed by is estimated by applying and measuring the probability of all the zeros outcome. One could estimate the L terms of the form, blah, blah, blah. All the unitaries. Instead, we introduce a novel circuit called the Harmonic overlap test that directly computes this without having to control V or U at the expense of doubling the number of qubits. This circuit is schematically shown in Figure 1 and explained in detail in Section 4. Cost evaluation, but where's the cost function then? The cost Hamiltonian. Cost functions. Cost functions. For simplicity, we write, as henceforth here, we discuss several reasonable cost functions. A simple intuitive cost function involves the overlap between the unnormalized projector with and the subspace orthogonal to be as follows. Why the simple intuitive cost function is the overlap between the unnormalized projector? But why does it have to be a projector? We note that one can view this cost function as the expectation value of an effective Hamiltonian blah, 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 which is similar to the final Hamiltonian reference 10. Each function is small if it's proportional to p, or if the norm of phi small, the later does not represent a true solution, and hence to deal with this, one can divide by the norm. Where is normalized state as shown in performs significantly better than, hence we believe that normalizing the cost is important for the performance of the VQLS. Okay, so basically the whole point here is I think I'm not really far away from the correct intuitive cost function, but it's apparently not performing the optimally, and so you kind of do some normalization here and there. Yeah, and that's kind of why you then need to compute those values. So normalizing the cost CG is important. Global cost functions such as those in 3 and 5 can have gradients that vanish exponentially in the number of qubits n as noted previously. To improve trainability for large n, one can introduce local versions of these costs, where the effective Hamiltonian because what this year, like I think I finally understood where the z comes from. So this year I was so confused last time. It's like, why these and why on qubit 3, right? And the reason is because, and that's what pissed me off, because that's not explained in the beginning of the text, but that's the idea is, that's kind of the example, right? It's the example that you're going to run these for. It's solving for these. So this is A. And so you can see that the way you construct A is by applying like a Z3. So it's the Z gate on the third qubit. And that's where this comes from. And the whole idea with gate sets in here is to actually make it programmable, configurable. So the idea would be, so you're putting like a 0 is an identity, and so no gate, and 1 is a Z gate. So, and that's why in the third qubit, so this is in the third qubit. Yeah, so that's why this is done. Control V. So what the Kiski textbook is going through is a simplified version of VQLS, which is only for real numbers, not complex numbers, and that's why they completely omit this extra phase in there, like this part in here. cost. That makes sense because the actual cost function. The goal of the algorithm will be to minimize cost. So they will when our cost function output very small. So no will projection Hamiltonian. So let's try to unpack that. I want to try to unpack that. Why is it the projection Hamiltonian, the one that's used? Because then this is where you unpack that, and you're doing the expectation value of these. So, and this is where all these terms come from, and then you're saying we notice that the second term tells how much lies along B, but when we then subtract these from another number to get the desired low number when the inner product is greater, they agree more. And the opposite for when they are close to being orthogonal. This is looking good so far. However, there's still one more thing we can do to increase the accuracy of normalizing the cost function. This is due to the fact that if it has a small norm, then the cost function will still be low, even if it does, even if it does not agree with B. Thus, we replace. So yeah, this is and kind of this is where you end up with. And so those are the two terms that you want to compute in this simplified version of VQLS, and that's how you. So this is calculated with a Harmonic test because this is just a Harmonic test is yeah. Estimate even some state expression value with respect to state or it's expectation value. I'm not like still super familiar with some of this notation, and that's causing me a bit of trouble. In here specifically, why the Hadamard test actually intuitively works here. Because we can implement this for the two values. I have to compute. So here are the coefficients. These are the coefficients of A. Where are AM and AN coming from? Every possible term using the Harmonic test is the first state. And then perform the control operations with some control circuit with the new geometries is AM and AN. We can implement these in code. And expand the form of these. Okay. And to calculate these, so this is expansion. This all looks just more complicated than it actually is. And it's just a complication added because of the notation. And so the Harmonic overlap test is a neat way to calculate that without adding an extra ancilla qubit. And we've seen this here. That's cool though, it's a really cool test. Yeah. The question is, yeah, it's probably not good enough. That's the whole point in here. Yeah. Am I happy? Am I happy with these? I'm not super. I don't know if I'm happy with these. Why are we calculating here the transposes? Why do we do it this way? This I also don't get. So CLAL. Okay, so the AL are those are these different elements that A is decomposed into. Size of preparing quantum state X suggestion is proportional to B or equivalently such that so this is you're trying to normalize this. That's why you wanna That's why you want to get that. What should we optimize to maximize the overlap between the quantum states? Is suggested you find the following cost function. First method, second method. Is to minimize the local version of the cost function, which is easy to measure and at the same time leads to the same optimal solution. This local cost function, which can be obtained by replacing the blue color projector with the following positive operator. This positive operator locally applied to the jth qubit. This gives a new cost function. Also, in this case, coefficients can be experimentally measured with the Harmonic test, the corresponding quantum circuit. Like, I understand the idea generally, but I feel I'm missing one level of detail to feel comfortable or happy that I want to move on with this. Kind of, we have, so we're having a cost. So you're preparing the ansatz, you're preparing U, and then you're doing different things. So you're doing a Hadamard test. What is it? Here. So you're doing a Hadamard test. Why do we uncompute though? But it's even L prime, so it's not like why. This is what this is a bit disturbing. This is okay. So I need to figure these out. Why are we doing it this way? And why here? Why are we also doing it this way? Why am I multiplying this with U? This I don't get. I get the Roth idea, and I think that that kind of work, but I don't understand the why are we controlling on this other term in here of A? Maybe I should literally do an example, follow the example in here to solve for these and try to understand. Maybe try to understand how this really works. This part, maybe. Because I understand the concept of the overlap test. I understand the concept of the Hadamard test. But I have a hard time understanding how is it applied here, especially these A's transpose things. Or is it just because of the expansion of the stuff that we want to calculate that they just show up in there? The inner product of 14. It's to compute the coefficients and calculate the inner product. Okay. I think the idea is because you're transposing it, right? Because you're trying to calculate the inner product. Are you? That's why you do it. Because remember, to calculate the inner product, right? Like if you've got like a vector like these, what you do for the inner product is you actually multiply by like the row version of it, right? That's the reason you're doing it this way. But wouldn't it be just easier if you can decompose that, like, and just do an overlap test with these? Why wouldn't these work? Why do I need all these other bells and whistles in here for this to work? Maybe it just would work, and this is a more optimal version, kind of. maybe I should just, maybe I'll try my naive version of it, see why it doesn't work, and I'll just pick a system of random system of equations out there just with real numbers, and I'll try to do this probably in the next couple of videos. So my attempt is going to be to kind of have not have these, see if it works, right? I mean, it doesn't have to be the most efficient thing in the world, but just to have these and kind of compute that part. I'll try it without these being variational. I'll try to kind of have a system where I already have a solution, and I'll try to kind of come out with that solution and see if the test overlap would just be enough. Maybe that helps. Kind of apply A, and then just this also not, and then just do the overlap test. Just have these elements in here, see if that works. Because I think I've got all the pieces kind of like in my head, and I know why and how this works, and I don't want to just get lost into the little optimizations here and there, because there seems to be a bit of that into this whole thing. How much time I've got left? Perfect, 50 minutes. So yeah, it kind of feels like that. Because there's normalization in there to make the cost function more efficient. There's a bunch of elements in there that are included just to make the whole thing work. If I get rid of these. It's like everything in life, right? Like you can come up with something intuitive first, and then you can use math to figure out how to optimize things. That's kind of how I feel about it. And I feel like I don't want to go that second step yet, but I want to understand if my idea works at all. On quantum hardware, see if my idea works at all. Cost evaluation. Effective Hamiltonian. Zero, right? A simple intuitive cost function involves the overlap between the normalized projector and the subspace orthogonal to B. Why the subspace orthogonal to B? This is confusing as well. I just say the overlap between the two things, right? So I don't care in what dimensional space I am, whatever n-dimensional Hilbert space or what. I just want to know the overlap. If the overlap is 0, it means they are, and then they can just be, different from a magnitude perspective. But if the overlap is the same, that's kind of the little bit that it's causing me also a bit of trouble. That can be its expectation of and here then you go with the optimizations of adding the normalization and etc. Right? That's why we want to calculate these. They have gradients that vanish exponentially in the number of qubits n. trainability, local version of these cost functions. What does it mean? What do they mean by local versions of these Hamiltonians, of these cost functions? So this is experimentally computable and satisfies. Hence, when training CG or CL, one can employ the right-hand sides of, as opposed to those of 9, as a termination condition. Furthermore, one can employ the operational meaning of the trace distance to note that for any P of M element M, we have this difference between expectation values. Relaxing to the general case where M is any Hermitian observable. Let us know. Number of proof for 9. Consider the first 9, whatever. Consider evaluating the term which can be written as, and these being German. L prima. Okay, L prima being, because this is what we're, yeah. Because here you're having a sort of a transposed version, so you're summing and multiplying each element of the matrix. Right? And so beta L and beta L prima are the same element in each of the matrices. But the one thing that I don't understand is where the zeros here come from. It's just because it's a zero state. Okay, anyway, so this is definitely bringing me some headaches, but I'll try it in the next video. I'll try to just basically pick one example and try out my idea without making it variational. So I'll just actually pick a system of equations of which I know a solution, and then we'll just try to see if the overlap test kind of would work, right? That would be, that's the idea, because to me it seems that's simple enough, but then I get it that, to really get it to work in a way that all the stuff you need is computable, and in a way that it just makes sense to use a quantum computer and not just something else, then you probably need to do all this, twisting here and there to find out a way to calculate a cost function that it actually works for your variational idea. Okay. But I don't like the fact that I don't fully understand that I can't fully follow that. So I'll definitely try to do another run on these, or I might just put it aside and then come back to it later on. But I definitely want to try an actual example. Perfect. See you next time.